Hello, in this talk I will address the problem of learning high-level symbolic representations from input traces with the help of such solvers. We will consider cases of learning models for classical planning and models for generalized planning from non-symbolic and symbolic traces over small problem instances. The learned models can be used for different purposes, such as to find plans for bigger instances, to do plan and goal recognition, or as building blocks for constructing more complex planning models. This talk is based on results from different research threads where I have collaborated with Hector Geffner and Guillaume Frances. The general problem that we deal with is the problem of learning a general and symbolic representation expressed as a model in a planning language that explains a set of input traces, where a trace is an interleaved sequence of observation tokens and action labels. Explains means that the model is able to generate the input traces, and general means that the model can also explain traces that come from bigger instances of the same task. This is a very general description, and we must make it concrete by throwing in assumptions and constraints to make the learning task a well-defined task. In particular, we need to put assumptions on the input set of traces, the target planning language, whether strips or other language, and what is meant to be general. Another important question is how the learned model can be used on new instances, for doing planning, for example, as this may involve to come up with interpretations of atoms from raw images. We want to learn high-level symbolic models because they convey crucial information for diverse tasks in a concise and clear way. As we already know, the model-based approach for planning is successful and robust. There has been a steady development of theory, method, and solvers, and the models can be understood, analyzed, and composed into more expressive and complex models. However, models are needed, and they often are complex and handcrafted. This is one of the main limitations for applying planning technology in real-world applications. On the other hand, deep reinforcement learning doesn't need full models and has shown impressive results, but the latent representations that are produced are opaque, difficult to understand or analyze, and often not general. Thus, learning models automatically is a step towards closing the gap between model-based solvers and model-free learners. Indeed, for example, learned models can be fed into deep learning approaches that learn general policies from planning models. The outline of the talk is as follows. We will consider three settings: the learning of first-order strips model from non-symbolic traces, and the learning of QNP model for generalized planning from symbolic and non-symbolic traces. Hence, after seeing how strips models are learned, we briefly revise QNP models and then see how QNP models can be learned as well. Let's see an example of how to learn a general strips model for the problem of towers of Hanoi. Let's consider as input a set of traces for Hanoi where the traces are non-symbolic, for example, given as sequences of images. Under the assumption that different states are associated with unique and different observations, the set of input traces can be summarized as a directed graph where each node corresponds to an observation and each transition in a trace is associated with an edge in the graph. In a Hanoi problem with 3 disks and 3 pegs, there are only 27 states and 78 transitions. Under the assumptions, the set of input traces is mapped into the shown graph. Then, only from this small graph, the following single action schema is learned or synthesized. It involves two different fluents: clear that tells whether a disk is clear, and not on that tells whether a disk is not on another disk. The schema also uses two static binary predicates that tell whether a disk is bigger than another and whether two disks are different. The strips model for this single schema is general. This means that it is correct for any instance of towers of Hanoi and any number of disks and any number of pegs. In summary, a set of traces is mapped into a directed graph, which is then mapped into a first-order strips model. Let's now formalize in clear terms what are the assumptions on the input set of traces. The most important concept is that each trace, which is an interleaved sequence of observations and labels, is associated with a hidden straight trajectory made of states and action, such that each state is mapped into an observation and each action is mapped into an action label. We say that a trace is non-symbolic when the observations and labels are flat, that is, they have no structure. For example, when states are given by images and action labels are just text strings. Otherwise, when observations and labels have a structure and information can be extracted from them, such as atoms or object names, or arity of atoms or actions, we say that the trace is symbolic. On the other hand, we say that a set of traces is complete if each possible transition in the instance is represented by a transition in a trace, and fully observable or free of confusion when each state is associated with a unique observation and different states are associated with different observations. Under the assumption that the input set of traces is non-symbolic, for example given by images, and is complete and fully observable, the input set can be summarized by a directed and labeled graph whose nodes are the observations and the labels are the action labels, and the edges come from the transitions in the traces. In Hanoi, for example, the input set of traces is summarized by the directed graph shown that has 27 nodes and 78 edges. The target class of models are those that correspond to first-order strips domain. Such a model is a pair made of a first-order language sigma that contains constant and relational symbols, and a set of action schemas, where a schema is given by an action name together with a vector of arguments, a precondition, and an effect. The precondition and effect are set of literals over the first-order language, whose free variables are among the arguments of the action. A Hanoi problem can be encoded with a language that includes one unary predicate clear and two binary predicates on and bigger, and with a single action schema, move disk from moving a disk from a source to a destination disk. The precondition is that the disk being moved and the destination disk should both be clear, and the disk should be smaller than the destination, while the effect is to move the disk from the source to the destination. In this encoding, the pegs are modeled as biggest disks that cannot be moved. On the other hand, a stripped instance for domain D is a tuple that contains a set of object names and set of literals that define the initial and goal situations. The object names extend the first-order language with new constants, while the initial and goal situations are variable-free atoms over the extended language. A strips model is a domain paired with an instance. Such a model spans a label and directed graph that is made of the states that are reachable from the initial state and label edge that correspond to the transitions induced by the model on the reachable states. A Hanoi problem with 3 pegs and 4 disks is encoded with the extended language sigma that contains 4 constant symbols for the disks and 3 constant symbols for the pegs, and where the predicate bigger has a static interpretation given by any peg is bigger than any disk, and disk di is bigger than disk dj, for I less than j. The initial and goal configuration shown then correspond to the given set of atoms, noting that the interpretation of the static predicate bigger is not shown. Since the input set of traces is summarized with the directed graph and a strips model also spans a directed graph, the learning task for a strips model is simply becomes the problem of finding a model such that both graphs are equal, or in mathematical jargon, isomorphic. Formally, for an input set T of non-symbolic traces that is complete and fully observable, the learning task for a strips model is the task of finding a model such that each action schema in the model is associated with an action label, and both graphs are isomorphic with respect to the action labels. That is, there is a one-to-one and onto map from the vertices of one graph into the vertices of the other graph such that the set of label edges for each graph coincide. In such a case, we say that the model M solves or explains the input set of traces. For example, the strips model for Hanoi explains the input set of traces for Hanoi. In general, we are not bound to a single input set of traces. Given input sets T1 through Tn summarized by corresponding graphs, the learning task for a strips model is the task of finding a common domain D and instances I1 through In such that each model mi given by the domain and the instance I sub I explains the input set T sub I. If calligraphic T is a class of set of traces, a strip's domain D is general for T if for each set T sub I in the class there is an instance I sub I such that the model M sub I solve T sub I. Often a single and a small set of traces, like in Hanoi, is sufficient to learn a domain that is general for an infinite class T. However, in general, we cannot prove that a learned domain D is general for an infinite class, but we can verify that D is general for a finite subset of the class. In order to solve the learning task, we need to bound the infinite space of models. Observe that a strip model is made of a finite but arbitrary first-order language sigma, a finite but arbitrary set of action schemas, and a finite but arbitrary set of object names. However, for a vector alpha of hyperparameters that bound the number of predicates and their entities, the number of different atoms used in the domain description, the number of action schemas and the maximum number of arguments, and the number of objects, then the subclass of models that comply with alpha is finite, and thus can be effectively searched. Therefore, we can slice the class of models using an increasing sequence of vectors of hyperparameters. This defines an algorithm that at each iteration, a bounded combinatorial task is solved. If a solution is found, the process terminates with a solution. Otherwise, the next vector of hyperparameters is considered and another iteration is executed. To make this algorithm into a real and practical algorithm, the outer loop is stopped after a sufficiently large vector alpha. The fourth step is a crucial one that defines a bounded combinatorial task. We solve this task using SAT. However, the underlying principle of finding a model that defines an isomorphic graph is a novel and crucial idea, and the method of how to find such a model can be implemented in many different ways. We now sketch what is the SAT theory that solves the bounded combinatorial task. For a vector alpha of hyperparameters, the SAT theory is partitioned into layers. The first or zeroth layer encodes the general first-order domain D, and there is one additional layer with index I for each input graph G sub I. A solution for layer 0 defines the domain D, while a solution for layers 0 and I defines an isomorphism between the input graph G sub I and the model graph G sub M. The propositional SAT theory thus consists of n plus one subset of clauses, such that propositional variables are only shared between layer 0 and layer I for each index I. To encode the domain in the first layer, we use the bound in alpha for the number of distinct first-order atoms in the domain. Each such atom is assigned to an indexed M proposition. We refer here to the ungrounded atoms that appear in the action schemas, atoms such as on X, Y, clear Z, etc. With this provision, the encoding becomes a standard one. There are propositions that define the mapping between action schemas and the action labels that appear in the input graph, propositions that tell which atoms appear as positive or negative preconditions or effects in each action schema, where the number of action schemas is bounded by alpha, propositions that tell the arity of each relational symbol, where the number of such symbols is also bounded by alpha, propositions that tell the type of first-order atom each one is one of the M atoms, that is, to what relational symbol it refers, and for each argument to what action argument or constant it refers, and propositions that define the unary and binary static relation used in the action schemas. This is done by assigning a schema argument to static relation arguments. The formulas in the theory guarantee that a satisfying assignment for all these propositions uniquely define a consistent first-order domain D, and that each first-order domain D that complies with the parameters in the vector alpha can be encoded with a satisfying assignment of the propositional theory. The strip's instance I sub I plus the domain encodes the model M sub I. The number of objects in the instance is given by hyperparameter in alpha. This number defines the grounded atoms that may appear in the instance, which are enumerated using k-atoms. Here we refer to grounded atoms of the form on A, B, on A, C, clear B, etc. The theory for layer I is encoded using propositions that tell which grounded atom is referred by each k-atom, propositions that tell the interpretation of each k-atom at each state of the input graph, and propositions that tell the valuation of the static grounded unary and binary predicate for the instances. For example, in Hanoi, these propositions indicate which disks are bigger than others. The formulas in the theory assure that a satisfying assignment defines a consistent instance for domain D, and that any such instance can be captured by a satisfying assignment of the theory. The final part, also in layer I, defines the isomorphism between the input graph G sub I and the graph defined by the encoded model M sub I. It features propositions that map transitions into the input graph to actual schemas, propositions that map grounded atoms in the instance in the form of k-atoms to ungrounded atoms in the action schema in the form of m-atoms, and propositions that tell which grounded action schema exists in the graph for the encoded model. The formulas guarantee that a satisfying assignment for the theory corresponds to an isomorphism between the graphs. A crucial aspect of the isomorphism is that the missing edges in the input graph must be justified, something that is done with the help of the static predicates. It can be shown that the whole set theory is sound and complete, that is, a satisfying assignment solves the learning task, and that if there is a solution to the learning task that complies with the hyperparameters in alpha, then there is a satisfying assignment that encodes it. Let's see some examples. For the problem of towers of Hanoi, the learner is given as input a set of traces whose graph corresponds to the complete state space for a problem with 3 pegs and 3 disks. This graph has 27 states and 78 edges. The learner outputs a model that contains a single action schema which can be shown to work for any instance with any number of disks and any number of pegs. The output model is not exactly the one that we saw before. In this model, the on predicate is replaced by the not on predicate. There is a superfluous binary static predicate, the ordering of the argument in the schema is not the same, and there is also a superfluous precondition. Let us now consider the standard gripper domain where a robot with grippers can move balls between rooms. The input set of traces correspond to a problem with 2 rooms, a robot with 2 grippers, and 3 balls. The graph has 88 nodes and 280 edges, and the action labels are either move, drop, and pick. Given this input, the learner outputs the model shown, which has 3 action schemas, one for move, one for drop, and one for pick. Observe that the domain needs to have at least 3 such schemas, since 2 different action labels cannot be mapped to the same schema, but it will have more action schemas, since 2 different schemas can be mapped to the same action label. Also notice that there is one static binary predicate con that tells room connectivity and another static predicate pair that tells object types. This is so because our target language for strips doesn't support object types, yet the framework theory could be amended to include such types. The solution found by the learner contains more information than the one displayed here. Indeed, the first thing to notice is that the solution also corresponds to a vector alpha of hyperparameters, the one that defines the solved theory. And the solution also tells us how many objects are in the instance, and in this case, their types. That is, the solution to the set theory not only identifies the model, but also identifies that the input set of traces correspond to a problem with 2 rooms, 2 grippers, and 3 balls. This is remarkable. Only from the input set of traces we are able to identify a correct first-order strips model that work for any number of rooms, grippers, and balls, that the input graph corresponds to a problem with 2 rooms, 2 grippers, and 3 balls, and it gives us the configuration of each ball, gripper, and location of the robot at each state of the input flat graph. Another example corresponds to an input set of traces for a small Blocksworld problem with 4 blocks. The input set of traces is mapped into a graph with 73 nodes and 240 edges, and with action labels move to table, move from table, and move. In this example, the underlying Blocksworld is one where the gripper is not modeled, but this is not explicitly said in any way. This information is implicit in the graph for the input traces. A graph for traces that come from a problem where the gripper is modeled would have more nodes and more edges. Given the input set of traces for 4 blocks, the strips learner outputs a model that has 3 action schemas, and it is correct. It works for instances with any number of blocks. The encoding found by the learner is quite interesting. It is different and more succinct than the standard human-crafted encoding. In the standard encoding, there are 3 predicates, one that tells whether a block is clear, another that tells whether a block is on the table, and another that tells whether a block is on another block. On the other hand, the encoding found by the learner only has 2 predicates, one that tells whether a block is clear, but in negated form, and another binary predicate that captures a disjunction. When both arguments are equal, it captures that the argument is a block not on the table, and when the arguments are different, it captures that the first is a block that is not on the second block. For those that know this domain well, there is also a human-crafted domain that has 2 predicates, clear and on, but that uses one additional object, named table, to capture when a block is on the table. The learned model doesn't need this additional object. As before, the set solution tells us that the input set of traces correspond to a problem with 4 blocks, and give us the configuration of the blocks at each state in the flat graph. With this example, we finish the discussion on how to learn first-order strips model from sets of non-symbolic but fully observable traces. We now change gears and move on to the problem of learning models for generalized planning. Generalized planning is about solving many similar planning problems at once, in one shot, by finding a general plan or strategy that solves them all. For example, to find a plan that achieves a fixed goal in any instance of Blocksworld, no matter the number of blocks or their initial configuration. The goal can be to remove all blocks that are above a given block, to put some block on another block, to construct a given tower of blocks, etc. The motivation for generalized planning is clear. Why bother to find a plan that solves a single instance when it is possible to find a general plan that solves an infinite number of instances? The problem of finding general plans is also a main line of research in other areas such as deep reinforcement learning, and it touches fundamental issues about representation and learning. Indeed, generalized planning sits nicely in the intersection of 3 important areas: planning, learning, and representation. In the model-based account, generalized planning provides a crisp theory and a convenient language for the synthesis of general plans. Qualitative numerical planning, or QNP for short, is a simple but expressive language for generalized planning. It permits to do several things at once. First, QNP models express a suitable abstraction for an underlying collection of planning problems. Second, the solution for the QNP are policies that solve all the problems in the collection. And third, using a reduction from QNP to font planning, the abstraction can be solved by off-the-shelf planner for fully observable non-deterministic planning problems. A QNP problem is similar to a strips problem, but extended with numerical variables that can be incremented or decremented qualitatively. Let's see an example. Consider the problem of removing all blocks above a given block X in Blocksworld instances. A suitable abstraction is defined by a simple QNP that has a Boolean variable h that denotes whether the gripper holds a block, and a numerical variable n that denotes the number of blocks above X. the initial state in the abstraction is not h and n bigger than 0, that denotes configuration where the gripper holds nothing and there is at least some block above x. And the goals in the abstraction are the states where n is 0, that denotes a configuration where there are no blocks above x. In the figure, there are three states together with the value of the variables in the abstraction, assuming that the abstract block x is the block A. In the first state, for example, the gripper holds nothing and there are two blocks above A. This state does correspond to the abstract state given by not h and n equals 2. An underlying assumption of this abstraction is that the value for the variables can be computed from the representation of the states, whether such representation is symbolic, as in strips, or images, as given here. The actions in the QNP are the following. The action put away that puts the block being held in some place not above x, and that is represented with precondition h equals true and effect h equals false. That is, to execute put away, the gripper must be holding a block, while its effect is that the gripper holds nothing afterwards. The fact that no other variable appears in the effect means that no such variable is affected. In particular, the variable n is not affected by the action put away. The action pick above x that picks a block above x that is represented with the precondition h equals false and n bigger than 0, and the effect h equals true and the decrement of the variable n. The action put above x that puts the block being held on the top block above x, that is represented with the precondition h equals true and the effect h equals false and the increment of the variable n. And the action pick other that picks a block that is not above x, represented with the precondition h equals false and the effect h equals true. In the figure, we see example of transitions given by these actions. The QNP defines an abstraction that has four states, the evaluations for its literals, regular literals h and not h for the Boolean variable h, and the literals n equals 0 and n bigger than 0 for the numerical variable n. These two literals are complementary to each other, namely, one is the negation of the other. In the abstraction, the increments for a variable x become deterministic effects that make true the literal x bigger than 0, while the decrements for x become non-deterministic effects that make true either x equal to 0 or x bigger than 0. For example, the action pick above x induces two edges in the abstraction. This action is only applicable at the state where h is false and n is bigger than 0. The effect of pick above x is to make h true and to decrement the variable n. Then there are two transitions associated with pick above x. Both transitions make h true, but the first makes n equal to 0 and the second makes n bigger than 0. Therefore, a QNP with n variables defines in compact form an abstraction with an exponential number of states. For this simple abstraction, the solution implements a loop that picks blocks above x and puts them away until there are no more blocks above x to pick. Formally, a QNP is a tuple that specifies a finite set of Boolean and numerical variables, f and b, description for the initial and goal states, I and j, and a set of abstract actions. Each action has a precondition that is made of literals, and an effect that is made of literals for the Booleans and qualitative increments or decrements for the numerical variables, with the condition that if the action decrements the variable x, then the precondition must include the literal x bigger than 0. Different from numerical planning where variables can be affected by exact amounts, the numerical variables in QNPs can only be affected qualitatively, that is, by uncertain positive amounts. This is a crucial difference between numerical planning and qualitative numerical planning. Indeed, this difference makes the plan existence decision problem for QNPs to be decidable, while it is undecidable for numerical planning. A sum abstraction for gripper is obtained with one Boolean variable t that says whether the robot is at the target room, A, and three numerical variables b that counts the number of balls still at room B, C that counts the number of balls being held, and G that counts the number of grippers that are empty. There are two actions to move the robot from room B to room A and vice versa. One action to pick balls at room B and two actions to drop balls, one at room A and another at room B. The actions that move the robot only change the Boolean variable t, and the others only change numerical variables. For example, the action pick at B has precondition t equals false and variables B and G to be greater than 0. That is, the robot must have a free gripper and B at room B, and there must be some balls still in room B. The effect of the action is to decrease the number of balls at B, decrease the number of empty grippers, and increase the number of balls being held. However, the abstraction has no action to pick balls at room A, since the transitions for such an action are not representable with the given variables. This poses no problem in this example because the abstraction is sound and has solution. On the other hand, a more complex abstraction where there is an abstract action to pick balls from room A is also possible. A solution for the QNP for gripper looks as follows. It basically implements an outer loop that moves back and forth between rooms. Inside the outer loop, there is an inner loop that keeps picking balls at room B while there are such balls and free grippers, and another inner loop that drops the balls being held at the target room A. Once the balls at B are exhausted, the robot moves to room A and drops all the balls it held in room A. This is a general plan that solves any instance of gripper that is problems with any number of balls and any number of grippers. A more complex abstraction that considers multiple rooms with multiple balls that need to be delivered at different destinations is also possible. The solution for a given QNP are the strong cyclic policies that terminate, where a strong cyclic means that every abstract state that is reachable with the policy is connected to a goal state via the policy. And termination means that every infinite trajectory that is induced by the policy terminates. An infinite trajectory terminates if there is a variable x that is decremented on the set of recurrent state, but it is not incremented in this set. In gripper, for example, any infinite trajectory whose recurrent states correspond to the first state of the outer loop terminates, because the variable for the number of balls at room B is decremented in the loop by the action pick at B, but never incremented. Therefore, at some point, the number of balls at room B becomes 0 and the loop terminates. QNP-based abstractions are expressive and effective. We now discuss how QNP models can be automatically learned from input set of symbolic traces. The main challenge when designing a model is to come up with the right set of variables. Once this is done, it is easy to come up with a set of actions that make up the abstraction. One way to get variables or features is to define them in terms of concepts. Concepts such as the number of blocks above block A, the set of free grippers, etc. Then, from a pool of concepts that define a pool of features, the learning task becomes a combinatorial task of selecting a minimal subset of features that account for the transitions in a set of traces from small examples of the planning task. The input to the QNP learner is the strips domain that defines the language, a set of sample traces, and an integer n that bounds the complexity of concepts. The output is a QNP model that explains the traces or failure if such model doesn't exist. The method is as follows. First, the atom schemas from the domain are plugged into a fixed concept grammar to generate all concepts with complexity bounded by n. Each concept defines a feature that can be Boolean or numerical according to the states in the sample. The feature for concept C is Boolean if its denotation has cardinality always at most 1. Otherwise, the concept defines a numerical feature whose value is the cardinality of the denotation of the concept. The pool of concepts then define a pool of features. Using the set of traces and the pool of features, this ASAT theory is constructed whose solution defines a subset of features that separate the states and transitions in the traces. Finally, from solution to the theory, a QNP model Q that is sound for all traces in the input is obtained. The SAT theory is quite simple. It contains propositions of three types. Selected F that define the selected subset of features, propositions D1 S, T that are true if the state S and T in the sample are separated, that is, distinguished with the selected subset of features, and proposition D2 for two transitions in the sample that are true if the transitions are separated with the selected subset of features. The formulas are also simple. First, positive units D1 for states S and T such that only one of them is goal. This enforces that the selected features must separate goals from non-goal states. The second type of formulas express the restriction that if some transition that comes from one state S is different from all the transitions that come from another state T, then the state H and T must be different. The last two types of formulas are just the definition of D1 and D2. The first says that two states are separated if at least one feature that separates them is selected. The second formula is the analog for transitions. The result is then that the theory is satisfiable if and only if there is a sound QNP abstraction for the sample that is given in terms of a subset of features from the pool. Recovering a QNP model from a satisfying assignment is straightforward. The features in the model are those selected by the assignment, and for each transition in a trace, there is a QNP action whose precondition is given by the source state of the transition, and the effect is given by the value change of the selected features across the transition. Often, many actions can be collapsed into a common action by simplifying preconditions, a check that is easily implemented. Let's see a couple of examples. In the first one, the QNP learner is able to learn a general QNP model for gripper, similar to the previously seen. The model is learned using a small set of traces containing 403 transitions and a small pool of features made of 130 features. The difference of this model with the previous one is that the learned model does not have the drop at B action, which is not used in the solution, but it has two actions to move to target room A. One action that moves when the robot cannot carry any other ball because it is full, and another action that moves when the robot still has capacity to carry more balls. These two actions are not really needed, but they are the outcome of the learning process. The learned model is sound for instances with any number of balls and any number of grippers. The model is solved by reducing it to font problem, and then using the font SAT planner. The whole process, from sample to solution, takes a few seconds. The solution is similar to the previous one. It implements an outer loop that moves the robot back and forth between the rooms, and two inner loops, one that picks balls at room B and another that drops them at room A. In the second example, we consider traces for a problem where an agent navigates a grid with blocked cells in order to collect rewards that are distributed on the grid. The input set of traces contains 568 transitions and the pool of features contains 280. The trajectories in the sample are obtained from two small problems with grids of dimension 4x4 and 5x5 and different rewards on blocked cells. In this case, two numerical variables are learned: the number R of reachable rewards that remain in the grid and the distance d to the closest reward along an unblocked path. The learned model contains two actions. The first moves the agent towards the closest reward by decreasing the distance d, and the second collects the reward and decreases the number R. The collect action also increases d. This increment that works as a reset sets the value of the distance to the next reward to be collected. When all the rewards are collected after the last collect action is executed, the variable R becomes 0 and the task ends. The learned model is sound for any instance of the problem, that is, for any grid size, any number of rewards, and any configuration of blocked cells. The solution is obtained by reducing the model to font and solving it. Everything learning and solving is done in few seconds. The solution implements an outer loop while there are still rewards to be collected and an inner loop that moves the agent to the closest reward. There are many other examples, and using a new set formulation, we are now able to synthesize models for generalized planning in an improved way. We now turn to the last part of the talk, where we discuss how to learn models, QNP models, from input set of non-symbolic traces. QNP models are so expressive that a single numerical feature n that counts the number of steps to reach the goal, and a single QNP action that decreases n when bigger than 0 is a correct model. Such a model, however, lacks a structure, and the computation of the value of n is intractable in general, since it involves the computation of distances in an implicit graph. To get meaningful models with a structure, we assume that the given traces have been annotated by a teacher. The goal is then to learn a QNP model that explains the teacher. We assume a teacher that marks transitions as good or bad. A good transition is one that the teacher would execute at a given state, while bad transitions are those that the teacher will not take. The teacher also assigns labels to good transitions, such as peak, drop, etc., and assigns colors to a state, at least to distinguish goal from non-goal states. The teacher may also use other colors to indicate, for example, that some states are similar because they represent the achievement of some landmark. Under these assumptions, the set of input traces define a graph, such that the subgraph spanned by the good transitions make up a directed acyclic graph, where each path leads to a goal state. Bad transitions are cross or back edges on the DAG, and the states are assigned to different colors. For example, the slide shows DAGs for two sets of annotated traces. The DAG on the top corresponds to a Blocksworld problem with 4 blocks, where the goal is to reach a state where the block A is on block B. States in green are goal states, but the teacher also uses yellow, purple, and orange. The color yellow, for example, marks states where both blocks A and B are in the same tower, while the color orange marks states where both A and B are clear and the gripper holds nothing. These states are deemed important by the teacher, who decides to mark them apart. The DAG on the bottom corresponds to a delivery problem for a 3x3 grid with 2 packages, where the agent needs to pick the packages and deliver them at a designated target cell. The states in green are goal states. In this case, the teacher uses only one color. Since transitions are marked as good or bad, the policy is already hinted by the teacher. Any selection of good edges at each state is a valid policy. However, the policy must be captured in the form of a QNP solution that must be defined by a set of Boolean variables, a set of numerical variables, and a set of QNP actions. As before, the target class of QNP model is sliced into finite subsets using vectors of hyperparameters. Each such vector bounds the number of Boolean and numerical features and the number of actions in a QNP model. Moreover, in order to guarantee policies that terminate, the learning focuses on the set of regular policies, where a policy is said to be regular when there is an ordering of the numerical variables such that if some action increases a numerical variable, then it decreases another numerical variable that comes afterwards in the ordering. Then, like for the strips learner, the task of the QNP learner is to find a model and solution that defines a graph that is isomorphic to the subtree of the annotated DAG. The whole construction ensures that the QNP is well formed, has a structure, and the policy is a strong cyclic and terminating. Each bounded combinatorial task is solved using SAT like for the strips learner. Without entering into detail, let me illustrate the type of models and solutions that can be found. In the top, the QNP learner finds a model for the generalized problem on A, B that consists of putting block A on block B in Blocksworld. The model has two booleans and two numerical variables. The model and policy are general and can solve any Blocksworld instance with any number of blocks and from any initial configuration. In the bottom, the QNP learner finds a model for solving the delivery problem that consists of delivering packages that are in a rectangular grid to a designated target cell. The model has one boolean and three numerical variables. The automatic learning of general planning representations from traces is a step forward towards bridging the gap between model-based solvers and model-free learners. The learned models are general and can be used in different ways. When learning from non-symbolic traces, the underlying principle of finding a model that defines an isomorphic graph to the graph defined by the traces is simple and powerful, independent of the target class of models, and can be solved in different ways. So far, we use SAT. Models for generalized planning can also be learned from symbolic traces, and the resulting models are solved using off-the-shelf font planners. We didn't have the time to discuss important issues. First, how to relax the assumptions about full observability and completeness of the input set of traces. The latter is not so difficult, and the former is more challenging but needs to be addressed for tackling more interesting problems. We have shown algorithms that learn first-order strips and QNP models, but didn't discuss grounded strips models nor other target planning languages. Last but not least, we haven't discussed the grounding problem. In non-symbolic settings, it is not enough to learn a correct model. We need to learn functions that provide interpretation of atoms from raw images. Learning first-order planning representation is a long-standing issue in planning. There are related works that learn such representations assuming symbolic information on the input, like predicate names and addities, number of objects, etc. This includes approaches based on inductive logic programming. On the other hand, there are systems that learn grounded representations for fixed-size domains, but it is not clear how such representations can be used on instances of different size. Recently, working on first-order models, there are deep learning-based systems that are able to learn general policies. These systems address the grounding problem. In the area of generalized planning, there are different works related to QNPs. Finally, deep reinforcement learning techniques has been successfully used to derive general policies, but the latent representations lack important desired features, and it is not clear how general are such techniques. We are currently working on different threads related to this work, among them, how to relax the fully observable assumption on the traces, and how to address the grounding problem in a general and principled way with the help of deep neural networks. The remaining slides contain the references. Thank you for your attention.